And okay, so last time we compared this to design, and based on this slides, we can easily see like which one is better, right? Which one is able to provide more information about the R, which is the thing we're interested in. So we try to estimate this R. So F2 design is better because it can give us like more resolution to get better estimation of this R. Okay, and now we move to some like more real situation. So in the real experiment, so for example, for some category, for example, for this one, actually this category consists of two categories, right? So either, do you still remember that 4x4 table? So the category 1,3 and the category 3,1 actually has the same. They have the same genotype like this. So that's why these two categories actually cannot be distinguishable. So this will bring in a little bit like more difficulties in the calculation. So we call this case as the calculation using the observed data. So not the perfect data, but the observed data, where some categories have the same genotype, such that they cannot be distinguishable from each other. So any questions here? Okay. All right, so in this case, we still use the same strategy. So we have learned this before. We use the likelihood function, the log likelihood function, to express the likelihood, right? The same thing, but instead of using the 16 categories, I hope you still remember. So by the 4 data, the ideal data 4x4, we have 16 categories here. But now, since we only observed the 9 genotypes categories here, so we here the log likelihood function consists of the sum of 9 terms here. So that this is how we write the log likelihood function here. And so we do the same thing. So we take the first derivative for the log likelihood in terms of the R, the parameter we want to do, right? We call this first derivative is the score function, and we set this guy equals to 0. And then when we solve this, so we can get the MLE, right? This is what we do. But in this case, as you can see, the score function, the first derivative is quite complicated. It's not a short and a concise form. It's not in a short and concise form. So, which means it's not easy for us to solve the R, even we set this first derivative equals to 0. So instead of using the regular MLE, we use the Newton Raphson method, the iterative method, to help us to solve the R hat. So any questions here? All right. So this is the core for the Newton Raphson method. So we use this Taylor series expansion. Yeah, this is very scary, but after I explain this to you, so it's not that hard to understand how where this equation came from. All right. So if you just look at this part and this part and this part, so we can rewrite this as this. So if we want to take the difference between SR and SR0, so that's the difference. So suppose this is the difference, and the denominator is the R minus R0. So what is this? This is actually the slope, right? So we want to, so if you treat the numerator as the y2 minus y1, and if you treat the denominator as the x2 minus x1, then this is just like slope of a curve, right? And this is exactly what this term refer to. So I hope you can see the relationship. So the difference between these two divided by the difference of these two equals to the slope, which is the second derivative at this point, right? Any questions here? Okay, good. All right, so if we understand this, then another thing is like when we try to estimate the R hat, right? So we usually set the first derivative when R equals to R, we set this guy equals to 0. So then if we set this is 0, we can easily solve this for each iterative step, right? And if we rewrite this part a little bit, we can express R. Oops. We can express R by using this equation. So if you just set this thing, the whole thing equals to 0, this is what we do in the MLE, right? And if you rearrange this equation a little bit, put R on the left-hand side and everything on the right-hand side, you can have this. So this is a beautiful iterative equation. So which means at the first step, we have a value, realized value of R. But if we want to calculate the next step, the value of R in the next step, so this is the equation. This is how we use the current R value to express the R value in the next step. So iterative, right? And if you just rewrite this a little bit, you got this. So at that time equals to t plus 1, how we calculate the R value. So the R value at the t plus 1 time equals to this formula using the value of R at the time of t. Which means like, so this is what we commonly use in statistics or mathematics. We use the iterative stuff. And if we have an initial value, arbitrary initial value for R0, then even you give a, so for example, so this is what we want to estimate using the iterative Newton-Raphson, right? So because you don't know the real R value, so you just give the program a initial value. So for example, so this is the real value R here, and you give the program an initial value which is a little bit far from the true value, but after the iterative algorithm, so it can so this algorithm can converge to the real. As the iterative process goes on, this method can converge at the real value R. So once the program converges, then automatically you get the estimation for this R. So this is how we use the Newton-Raphson iterative method to help us to estimate R. So can anyone tell me why we, so this is important. So can anyone tell me why here we do not use MLE, but we use the Newton-Raphson iterative method to help us to solve this guy? Can anyone?
Because you're missing data?
Yes. Very good. So yeah, that is the keywords I would like to introduce. The missing data. The missing data is like, for example, because last time we talked about like in an ideal situation, we can distinguish these two categories, then we do not have any missing data, right? But in this situation, we only observe the 9 genotypes category. So which means like these two are missing. We only observe the sum of these two, but not for these two categories specifically, right? So in this case, yes. So if missing data exists, usually there's not a simple, easy solution for MLE. In other words, if you try to set the first derivative equals to 0, so this is what we do for the MLE, right? And you're going to get a terrible formula rather than a simple, easy formula that can be solved. So then instead of finding the solution through this way, so we use the Newton-Raphson iterative way to do this. So this is the point. So in the final exam, if I ask you a question like, so in what situation you have to use something like the Newton-Raphson method to solve your R, to get the value, to estimate the value of R, then yeah, this is the answer. So if there's a missing value, if you cannot easily solve the first derivative, the score function of R, then yeah, we use this kind of like iterative thing to help us to get the answer. Okay. All right. So in statistics, so I hope everybody can develop a good habit. So once you you can successfully estimate something, for example, you got this estimation when the whole process converges at some point, then you get this estimation, right? But at the next step, you have to estimate how accurate your estimation is. So, which means like you have to also estimate the variance of your estimation. So on top of the estimation of R hat, you also need to calculate the variance of R hat. So in this case, it's easy. We have talked about this, right? We can usually get the information matrix for the R estimation, and this information matrix, the inverse of this information, will be treated as the variance of the R hat. All right. Any questions here?
Yeah, I just had a quick question. When we're studying the Newton-Raphson method, so in addition to knowing when to use it, what should we try to study when looking at the slide? Should we just try to understand the entire derivative?
Oh, no, okay, good. So you sorry, Adrian, your Wi-Fi is not that stable. I heard like your voice is a little bit like discontinuous, but it's okay. I think I got it. So you asked me for this Newton-Raphson method. So what level you need to know, right? To prepare for the final exam. Yes. So you here I don't require you each of you to understand each step here, but so which means like in the final exam I will not ask you to write these equations for me. No, but you need to understand the reason behind it. So because last time we talked about like MLE is so beautiful, so we can usually use MLE to get the job done. So to get the estimation of R, or in some other project that we can easily use the MLE to get the estimation for any parameters of interest. But why we bother to use this like a scary method, right? So it is scary. So I will not ask you to write these questions in the final, but you need to understand when and why we need to use it. So the answer is like in some situation, right? As you just mentioned, if there's a missing value, so you cannot get a very simple and straightforward a solution for the MLE, then you have to use something like this to help you get some approximate solution for the parameter of interest. Is that clear?
That's clear. Thank you.
Okay. All right. So yeah. So this is only for your information. So here. Okay, so this is the first derivative, right? Because yeah, this is not easy, so that's why we use the iterative thing to calculate this. And this is the second derivative, and we can use the second derivative to get the estimation, the variance of the estimation. And so this is interesting. So when we try to compare this with the F2 design, when 16 categories can be observed. So this is the ideal situation, right? But now still this is F2, but we only observed 9 genotype categories here. So what's the difference? So the difference is like, so in this new situation, the real situation, this is the variance of the estimation, right? And okay, now if you treat this one as a constant here, then this becomes this, right? And do you remember this part? So what is this part? So this part is the variance when for the F2, when 16 categories can, all the 16 categories can be observed, right? So this is the variance we see before. When there's no missing value, when 16 categories, all the 16 can be observed. But here, if we only observe the 9 categories, then the variance is a little bit different. Is this multiplied by a factor? Can you see that? So what's the impact here? So because this is always greater than 1. So can anyone tell me why this is always greater than 1, this C? Remember, R is a value which is always greater than 0, but less than 1. Is that correct? No, it's always less than 0.5, right? Is that correct? So this is why this constant C is always greater than 1, because 1 minus this thing is always smaller than 1 minus this thing. So this ratio is always greater than 1. Or in another way, so if we are missing something, then the missing problem will increase the uncertainty, right? Then it will increase the variance of the estimation. Does that make sense?
Can you repeat that last part?
Yes, sure.
Thank you.
No problem. Okay, so to help answer this, so let's do this. All right. So last time when we compare the backcross design and the F2 design, so we got this results, right? This means like this variance is greater than this. Do you agree? If n is equal, if the total sample size is the same, which means if we have the same sample size, the F2 design is better than backcross design because of the smaller variance of the estimation. And in another way, it's like we can say this is equivalent to what we can say like this. So if we use the backcross design, the estimated R has more uncertainty than that from the the F2 design, right? Does that make sense? Because of this. Okay, now the same thing here. All right, so this part is the variance for F2 when 16 categories can be observed, right? But the whole thing here is for F2 with only 9 categories can be observed. So which means this variance must be greater than this, right? So the uncertainty associated with this is larger than this uncertainty. So the variance of the R estimated from the 9 category must be higher than the uncertainty that is associated with the estimation from this 16 category, right? So yeah, this is the cost of having the missing data. Right.
Now, would that coefficient C be like scalable? If, for example, if you have 9, 16, a different multiple of 3, would it change in magnitude, I guess?
You mean this C, right?
Yeah, yeah.
Okay, so this C is actually equals to this, right? So this depends on your real R. So suppose you are dealing with like,
That's right.
yeah, very small 2 region, right? This is close to 0, then so this is close to 1, right? But if you got a very if you are dealing with like 2 loci with large difference, then the R will be significantly greater than 0. Then this constant, this factor does matter, right?
Mhm.
Yeah, this is a good question. So this depends on the real R. Yeah.
Okay. Thank you.
Sure. Okay. All right. Okay, so this is a very nice method. You can see a lot of like application of this Newton-Raphson in either statistics, mathematics, or physics. So it's very useful, but there's a problem. So people found some like issues with this method. So especially when we deal with the second derivative. So if we do the H scores here. All right, and the inverse of this second derivative can be easily overflowed, which means like, so if there's some like, if R is close to either 0 or 0.5, so this value can be easily sometimes can go quickly to 0, and if we want to do the inverse of this guy can be infinitively large, right? So yeah, this is the one problem, the overflowing problem that is associated with the Newton-Raphson method when we calculate the variance of the R. All right, so this is the problem. So that's why we have a second version of the Newton-Raphson. So this is a modification of the Newton-Raphson, which is called the Fisher scoring method. The only difference is here. So this is not required, just for your information. You just need to know, yeah, they're different. And the Fisher scoring method is based on the Newton-Raphson. So the only modification is here. That's the Newton-Raphson equation, right? The Taylor's series expansion. So the only modification for the Fisher scoring method is like, for this part, Fisher take the expectation rather than the direct, the second derivative of R. So this expectation will give a very nice control about the calculation of the variance, and it solved the overflowing problem. So maybe I can give you a very small question in the final. So what's the difference between the Fisher and the Newton-Raphson? So you just can simply say like, okay, so the Fisher scoring method is based on, is a modified version of the Newton-Raphson by using the expectation of the second derivative rather than the direct the direct calculation of the second derivative, such that the overflowing problem can be nicely controlled when we calculate the variance of R square of the R hat. Any questions here? Okay, very good. All right, so this is just for your information. So when we do the coding, programming, so we often use the matrix format to help simplify the calculation. And this is the Fisher scoring method using, this is the matrix notation version for, for coding the Fisher scoring method. All right, just for your information. Don't worry about this. Yeah, it's very complicated here. All right, and okay, so let me move faster. All right, so the last one I would like to mention in this chapter is the EM algorithm. So this is very similar to the Newton-Raphson. Excuse me. Okay. All right. It is a very, actually, it's very similar to the Newton-Raphson. So the EM algorithm is a, I think it's even nicer than the Newton-Raphson, because it's a combination of the beauty of the MLE and the iterative algorithm. So in one situation, we can use this very nice EM algorithm. Usually when we have some missing data, for example, if we're dealing with like 9 categories rather than the fully observed 16 categories, then we have missing categories, right? Missing data. We can use this EM algorithm. So the EM algorithm is another type of iterative method. So as you can see, we also see this iterative graph, right? So this is how we use this graph to represent the iterative. So this graph shows like the x-axis represented the number of the iterative. Usually the first several round of the iterative is called the warm-up period or burn-in period. So the estimation looks like very, very unstable. But after the iterative, the number of the iteration goes to a large number, you're going to see the estimation become very stable. So we call this as a convergence. So it means like the estimation converges to a value that we are looking for. So this is the iterative algorithm. All right, so in the EM algorithm, the iterative is organized in this way. So we first initialize our parameter, and once, so you can give an initial value for this guy. Don't worry about the accuracy. So you can give a value which is very, very, which is very far removed from the true value. It doesn't matter. So this program can help you to find the real value very quickly. Once you have an initial value, so you can use the expected expectation to calculate the expected value for the missing data. Remember, we have the missing value, right? But with this parameter, with this initial value of this parameter, we can easily calculate the expectation of your missing data. Once you have the expected value of your missing data, you can easily, so then this becomes a 1. So when you have missing data, you only observe the 9 categories, right? But if you use the expected value to replace the missing value, then this becomes a 16 category problem, right? Now, since you have a fully observed data, no missing data for this step, so you can get a very nice solution for the MLE, right? You can use the M step, which is the MLE step. You can estimate R easily. Then you can update your R value. Is that right? So this is the second run. Once you have your updated R value, you can continue this process. So with this R, you can recalculate the expected value of your missing value in this step. Then once you have your missing value imputed, you just change your missing problem into a problem without missing value. Then you can reuse the MLE. Is that clear? So this is how we alternate these 2 steps in the EM algorithm to complete this iterative algorithm. Any questions? I hope I made it clear.
I got a little bit confused. Can you condense that explanation?
Could you say that again? I'm sorry, I cannot hear you very clearly.
Oh, can you explain the explanation a bit more?
Yes, okay. All right. So this EM algorithm is very interesting. So let's go one step back. 10 minutes ago, I asked you why when and why we have to use the Newton-Raphson, right? Because if we have a 16 categories, which is the fully observed data, then we can just use the MLE, right? Because the MLE can give us a very simple solution for the R hat. However, in the real situation, we only observed 9 categories. So we label these 2 situations as the full data situation or the missing data situation. So missing, fully observed. Okay. Because of this missing, so we have to use the iterative, right? The Newton iterative, Raphson. Okay. So this is the 2 situations. Okay, now the EM algorithm is actually a beautiful combination of these 2. So let's see how the EM algorithm solve this problem. So, okay, now, because we suppose we have this R estimated. So this is the initial value. So you just arbitrarily give a value to R, and we treat this as a known value. Now, when you have this R, you can easily solve this missing categories. So because you don't know the R, that's why you only observed this 9 category, right? I'm gonna show you why this is the situation. But with this R, you can easily change this missing situation, the 9 categories, into the 16 category, which is the fully observed data. All right, which means with this initial R value, you can use the expectation step to impute the missing value, right? Now, once you imputed the missing value, you just successfully change this 9 category problem into the 16 category problem. If you have the 16 category problem, that's the fully observed, then you can use the MLE rather than the Newton-Raphson, right? So this is one iterative step. Okay. Now, once you estimate this MLE in the second step, you can use this new value for this R hat to replace the initial value here. Does that make sense? So with the updated R hat value, you can redo this. So with this updated R value here, let me use the other color. You have already updated this value. Then you can redo this data imputation by using this expectation step, the E step. So you can update the missing categories in the second iterative step. Once you updated this missing category, for the second time, you change this missing data problem into a problem without missing data. So you again, you have the fully observed 16 categories, right? Then you can redo this MLE to update this R value again and again. So if you just do this circulation, you're gonna achieve this kind of like converge in this iterative EM algorithm. Does that make sense?
That makes more sense. Thank you so much.
Okay, sure. Yeah, I'm happy. Yeah, because it's kind of like messy, the slides, but I'm happy that I made it clear. All right, good. So at the beginning, it seems like very complicated, but once you appreciate the beauty of this EM algorithm, so it's very useful. This method is very useful. A lot of us, many of us often use this method to help us to solve the problem in computational biology. It's very powerful. Okay. All right, so let's take a look at this example. So I think, let me see. All right, so this is the original 16 category, right? So the table, the 4x4 is the 16, but in reality, so we only observed like 9 categories. So so the blue is 1 because these 2 categories cannot be distinguished from each other. The same like this 2, and the same like this 2, and this 2, and there are another 4 categories here. So we only observed 9 categories. So you can easily see like the 16 versus 9, right? Either the full data or the data with the missing values. All right. Then we can rewrite this into this the 3x3 table. So this is just showing the genotype for the first loci and then the genotype for the second loci and the combination of these 2. So this gives us like 9 categories. So this is the 9 category with missing data. So I'm gonna go quickly since you already watched a video from 2 years ago. And this is how we arrange these probabilities here, right? And so this is this is the likelihood. So this likelihood actually only involves 9 categories, missing values here. All right, 9, right? All right. So this is not required. Don't worry about this. So I just want to use this slides to make it clear. So how the EM algorithm works. But in the final, I could give you a short answer question, like just simply describe how a EM algorithm works when you have like missing data. So give me an example. Just you just use your language to describe this situation. Yeah. All right. So okay, so this slide gives us the idea, right? So for 16 category, if there's no missing data, then so this is the MRE. So very nice solution. But in the 9 category, because unfortunately these 2 cannot be observed. So then we can use the EM algorithm. So in the E step, the expectation step, we just plug in the expectation of this two missing variable, then we have the full data. We can easily use this MLE in the M step, the maximize step. So, all right. So in the calculation, it's very simple, as you can see here, because we want to calculate the expectation of these two missing, right? So it's actually this expectation is actually associated with this category. So here we are missing this two, right? And this two actually represent the recombinant progeny. And the total probability for this category is this plus this. This means like, so if you look at the 4x4 table, this category and this category represent the parental type, which means there's no crossover at all. So this is the probability. Oh no, sorry. This is the probability for this two. However, this two category missing one represented the recombinant, double recombinant. So the probability that is associated with this as this. So this is the total probability for this category. Then if we want to just calculate this value will be, this is the total number of the progeny observed in this category, right? So what's the fraction of this M22 represent this two category? So that's the fraction. This is the denominator, and this part represent the recombinant in the numerator. So is that clear? Any questions here? So we can easily calculate the expectation of this two missing data. And once we have this, we can use the MLE, right? Beautiful MLE, and plug in this two expected value, missing value here. Then we get the updated R value in one iterative step. Any questions here? Okay, very good. So I think, yeah, I'm done with this chapter. Okay, let's move to the next one. So before we move to this the next chapter, so any questions so far? Is that clear? Okay. Okay. All right. So this chapter actually, all right. So let me talk this a little bit. So in chapter 1 and 2, we are interested in estimate this, right? So basically, we want to calculate the genetic distance between two loci, right? Two linked loci. So by using either the backcross design or the F2 design. I hope you still remember so how we can design a backcross or the F2. And based on the data, we can easily calculate the R hat for this two. And this actually is a measure of the genetic map distance between these two loci, right? Okay, now if we can get the R between A and B, and if we can also get the R between B and C, so the third loci, and the same, right? With by doing the same experiment, either the backcross or F2, we can also estimate the R between A and C. Okay, now if we have RAB, if we have RBC estimated, and if we have RAC estimated, so how can we use this information to help us construct a genetic map for these three loci? So we want to find the positions of the three loci. We want to find how the three loci are arranged along a same chromosome, right? So this is what we're going to learn in chapter 3. Okay. All right. Okay. So suppose this is the real order. The three loci A, B, and C are actually arranged in this way. But we don't know, right? So what we can do is like we construct a, so we can perform a, let's say, backcross design, and we can get RAB, which is the distance between A and B. We can get RBC, and we can also get RAC, right? So based on our genetic assay, we can only calculate the recombination fraction between two loci. Once we got these three values, how we put them together to construct a complete map, genetic map for these three loci. So this is the first one that we can use to help construct the map. The sum of adjacent recombination coefficient. We call this SAR. All right, so this is, so if you look at your textbook, so this is the definition of the SAR, the sum of adjacent recombination coefficient. So we make the summation. So given a map, so for example, given a map, so if the three genes, if the three genes are arranged like this, then we're gonna make a summation of the R estimation for the adjacent regions. So for example, if ABC is the correct order, then this SAR will be defined like this. So we're gonna add RAB to the RBC, right? These are the two adjacent recombination coefficients. So if the real order is ABC, however, if the real order is ACB, C is sitting in the middle, then the SAR ACB should be defined as the sum of the RAC, because yeah, this is the RAC and this is the RBC, right? Like this. So this is how we define the sum of the adjacent recombination coefficient. Any questions here? And so since we do not know the real order, right? Then we need to calculate the SAR for this order and the SAR for this order, and or the SAR for this order. There's another possible order, right? Where A is sitting in the middle. And so for three possible order, we can calculate three SAR value for each of them, right? Respectively. And so which one gives the right order? So the one with the smallest, the minimum SAR value will define the right order of the three loci. All right. So specifically, when we have the data from the backcross or F2 design, okay, we can calculate. So if we are dealing with like three loci, so we can calculate the SAR value for three possible orders like this. And then we're going to compare the three values. And the smallest one, the smallest SAR value will define the right order, which means like in this case, if the real order is ABC, then we're going to see the SAR ABC will be less than the SAR value of ACB. So this is important. Sometimes I give a question like this in the final exam, and I will ask you to show me if the right order is ABC. So how do you demonstrate that the SAR ABC is less than the SAR ACB? Okay, so yeah, this is important. Okay, let me show you how to prove this. So suppose this is the true order, right? The ABC is like this, and then we have learned this before, right? If ABC is the right order, then how can we represent the RAC? So I hope you still remember the recombination between A and C means either there is a recombination between A and B, but at the same time, there's no recombination between B and C, right? So this is one possible situation. Plus, there's another possible situation is like if there's no crossover between A and B, but at the same time, there's a recombination between B and C. Then this also gives, this also gives the recombination between A and C, right? Is that clear? Any questions? I hope you still remember this, right? All right. Now, when you simplify this, so if you don't remember, yeah, you can go to the previous slides. I mean, probably in the chapter 2, we have talked about this. So if you simplify this, you're gonna get this, right? Any questions here? I hope this makes sense to you. Okay. All right. Now, let's calculate the SAR ACB. So suppose we want to calculate ACB. This order, we don't know if this order is correct or not. Then we need to get the summation of this RAC and RBC, right? Now, this is the real situation. In real situation, RAC actually equals to this. So you just replace this by this. You got SAR ACB equals to this part plus this. All right. And you can rewrite this equation a little bit like this. Okay. All right. Okay. So this is how we express the SAR ACB, right? And by definition, the SAR ABC is very easy, equals to RAB plus RBC. So this is the same here and here. So now the key point to complete your demonstration is we need to know the difference here, right? Because the SAR ACB and the SAR ABC The only difference is this part. Is this part greater than 0, less than 0? This make a big difference, right? So, okay. Any questions so far? So I think this is very straightforward. And if I ask a question like this, yeah, please demonstrate the SAR value for the right order must be less than the SAR value for an incorrect order. You only need to show me the derivation on this slide. Okay. All right. So now let's take a look at it here. So what is R? R is a value between 0 and 0.5, right? So this is what we know. Okay, so then this guy is greater than 0. How about this? Is this part greater than 0 or less than 0?
Greater than 0.
Yeah, greater than 0 because R is less than 0.5, right? Which means like 2 times 2R must be less than 1. So 1 minus this guy must be greater than 0. So the entire thing here is greater than 0. Which means this is greater than this, right? Bingo. So you can so once you write this steps, yeah, you successfully demonstrate that the SAR ACB is greater than the SAR value for the correct order. Actually, this is very important because we use this criteria. So here we just simply deal with like 2 loci, right? We use this criteria to find the right order for this 3 loci. But just imagine, so on the same chromosome, probably we have like maybe 100 loci. So how do you find an order? Right order? How do you find the right order to arrange all this 100 loci? The same thing. So we just use the same criteria. We repeatedly use this criteria to order all the loci on the same chromosome. Any questions here?
Yeah, so would we just assume it's SAR ACB for everything, run this formula, and then if it's a negative, that's the smallest one?
That's correct, yes.
Okay.
Mm-hmm. All right, any other questions? Okay, all right. So, okay, so this is the first criteria we can use, the SAR, sum of the adjacent recombination coefficient, right? So equivalently, so we can use other similar criteria. So for example, rather than using the R, we can use the distance, which is the average number of the crossover, right? Then we can use the SAT. And if we, instead of using the distance or the R, we can also use the likelihood. So we can get the summation of the likelihood between different pairs. And in this way, so we try to maximize, not minimize. So because likelihood, actually, we try to maximize the summation to find the right order. So in the final, I can give you some like multiple choice or something. So which one, so by using which one, which criteria to find the right map order, you need to maximize the statistic or the criteria. So this is the one you need to maximize, right? All right. Okay. All right. So let's look at this slide. So this slide actually is a very simple, easy situation. So suppose we're only dealing with like 5 loci. So 5 loci. On a chromosome, actually there could be many loci, right? But here we're dealing with like 5 loci, A, B, C, D, E. And so this example shows us like how we can, excuse me. So how we can use this so-called exhaustive search to find the global. Global means like the true order of these 5 loci. So since this is an easy case, we only deal with a very small number of the loci, 5. So we can calculate, for example, we can calculate the SAR value for each order, right? So for each possible orders here. So there are not that many, there are only 60 possible orders for A, B, C, D, E, right? So it's not that easy. So we can easily write a code to calculate the SAR values for each of these 16 and find the smallest one. So because for now we are we understand why we need to find the order that is associated with the smallest SAR value. So if we can calculate all the SAR values for all the 16 possible orders, then we can easily find the right order. Right? But the problem is like, as I mentioned, this is only a small baby or toy example. But in the real situation, so the number of the markers or number of the loci could increase like sharply. So for example, if we're dealing with like 5 loci, so we only need to calculate the SAR values for 60 possible orders. But for the 6 loci, so you're going to see 7 and 8. So this number increased like exponentially. So so if we're dealing with like many loci, so it's impossible sometimes for us to complete this exhaustive like search. Then people invented some like smart and a quicker way to do this. So this is only for your information. It is not required. Yeah, please read the textbook. Try to understand the rationale behind this. This is the heuristic search, and there's some like a simulated annealing. So yeah, it is very fun to read this part. So just make sure you understand. So this is not required for your final exam, and some method here. But some method can guarantee to find the global optimal. Means like some method can guarantee to find the true order for the loci, but some cannot because there's a trade-off between the computational complexity and the accuracy. So sometimes to achieve like the computational efficiency, so some method cannot guarantee to find the global optimum, but it can find like local optimum, which is very close to the real order of the loci of interest. Okay, so I'm going to leave this part to you. So please read the textbook. Okay. All right, so I think the last thing for this chapter is to, I'm gonna talk about the bootstrap. So before I talk about the bootstrap, so I am gonna spend a few minutes to talk about some like very basic concepts in statistics. I believe many of you have already learned this in your statistics class, but yeah, to help us better understand our stuff in this class, so I'm gonna very briefly review this part. So what is statistic? Statistic is actually a scientific method that we can use to make inferences about the population of interest. So suppose we are interested in this population, and let's say like the population mean. For example, if we want to calculate, if we want to know about the average height of human beings on this planet, the best way is to measure everybody's height, right, and get the average. But that is impossible because the population is too large. Yeah, it is impossible for us to do this kind of like exhaustive like measurement. So usually what we do is like we take a small sample, but this sample must be a random sample. Why is that? Because only the random sample can unbiasedly represent your population, right? And then, okay, so the goal is to make inference for your population, but since we cannot study the whole population, which is too large, so we take a small sample and we just study this sample, and then we assume this sample can represent this population. So, okay, now when we have a sample, we can easily calculate the sample mean, right? Sample mean is called a statistic, one type of statistic. We use this statistic, which is summarized from the sample, and go back to make the inference for the population. So here, actually, we are interested in the population parameter, which is mu. This is the thing we're interested in the population, but we don't know this guy. Then we take a small sample. We use the sample mean, which is the X bar. We call this X bar as a statistic, and we use this to make the inference for the population mean, which is the parameter. So this is a statistic, and this is the parameter. We want to use the sample statistic to infer the population parameter. So this is what a statistic do. All right. Okay, so basically, so in statistic, so if we want to study the population parameter mu, we can take multiple samples, right? We can, for example, we can take a random sample of size n and calculate this sample mean, which is the statistic to infer this mu. We can do the same thing. We can take another random sample, which is different from the first one, right? And this sample statistic might be a little bit different from the statistic you got from the first sample, and so on. All right, suppose you can afford multiple samples here. And for each sample, you can get a sample statistic. If you plot your sample statistic, this is called the sampling distribution. And this will give you the variance of your sample statistic, X bar, right? So this is the very basic thing for statistics. Okay, now in our study, so we need to understand what is the bootstrapping. Sorry. The bootstrapping is some situation is like this. So we only afford one sample, one random sample from the population. We cannot afford another sample. Then from the single sample, we can only get a single sample mean, right? Statistic here. So how can we estimate the variance of this estimation, this statistic? So since we only have one single sample, what we often do is to do the resample, or called the bootstrap. So for the single sample, you're going to see the distribution of your sample values, right? And this single sample actually shows the distribution of the population. So what we do is like, so for example, this sample is of size n. We can generate a lot of resamples of size n from this single sample of size n. So let's look at this. So how we generate the first resample of size n from this single sample of size n. Okay, so from this sample, we randomly take one individual from this to form the first value in this resample. Once we got this, we put this value back into the original single sample, and we do this again. So it's likely like the first value will be resampled from this original sample, right? If this value is highly frequent in the original sample. So okay, now we sample the second one from the original sample for the first resample, and so on until we call this replacement sampling with the replacement. Once we got any value from the initial sample for the resample, we put this value back to the original original sample. Sorry. Is that clear? Any questions? All right. So by doing
real
this,
quick, can you
yeah.
give me an example of even a thought experiment of like how you would do that? Like, let's say for height, for example, if you decide the height of one person, how do you bootstrap that?
Sure. Okay. So suppose this is your example: 1, 1, 2, 2, 2, 2, and 3, 3, and 4. Okay. So this is your single sample, just like here. And this sample actually already reflect some nature of your population, right? Okay. Let's see how we can generate the first resample. I use the resample here from this sample. So, okay, now for the first value, you just randomly choose a value from here. So let's say you got a 2 from this sample, okay? And okay, now you got the first value of your resample 1, but you put this, so you take this 2 from here, right? Okay, but for the second value, you have to put this 2 back to the original sample, which means like for the second value, you still sample a single value from this original sample. We call this sampling with replacement, because for the first value, you already took this 2 out, right? But for the second value, you have to, before you take the second value, sample the second value, you have to put the first sample 2 back to the original sample to do this. So it's very likely the second time you got another 2, right? Because the 2 actually are the most like frequent value you saw from your original sample. Does that make sense? Okay. So for the third one, you also got a 2, but for the fourth one, probably got a 1. You put this one back as well. How many? 1, 2, 3, 4, 5, 6, 7, 8, 9. So the sample size is 9. So you do this probably. Okay, now once you got this, you successfully did a resample. The first resample, sorry, from your original sample. Does that make sense? You're gonna see like it's different from the original sample, but it's somehow very similar to the distribution of your original sample, because you just sample the values from your original sample. Does that make sense? Okay.
Yeah, it makes more sense. Thank you.
Yeah, so so once you got the first resample, you do the second resample, the same thing. Now this time probably you got a different like things. So you got 1 first, and it got 2, you got 2, you got 1, you got 2, you got 4, you got 3, you got 3 again. 1, 2, 3, 4, 5, 6, and you got another 2. So this is your second, and you can keep doing this, generate a lot of like resample. Okay, now. So you, the purpose, the point of doing this resample is like, because if you only have the first sample, you can only calculate the sample mean, which, so for example, you got a sample mean equals to, let's say, 2.3. But based on a single sample, you cannot get the variance of this X bar, right? That's very awkward. So you can get your estimation, but you cannot but you cannot estimate how accurate your estimation will be. So that's why the smart people like invented this method, so do the resampling. So once you have a lot of like a resample, so for each resample, you can calculate a X bar for this one, and use another one, X2 bar for this sample. And all this X bars for those resamples gives you an idea about the variability of this estimation. Does that make sense? Is that clear? Good. All right. Very good. So now, once we have this idea, so it's easy for us to know how we can use this bootstrap to construct a confidence interval or the confidence level for our map. So now I try to bring you, drag you back to our business, right? So here we try to, for example, we try to use a, let's say, backcross design or a F2 design to get a lot of data, so we can construct a map like this. So suppose this is the map we got from our experiment. All right. So suppose, so now we have like the order of 5 loci, but we are more interested in this. We want to find if these 2 loci, let's say gene B and gene D and gene B are linked or not, tightly linked or not. We want to see if they are tightly linked. Then we can leverage the bootstrap method to help us find the confidence of this map order, right? What we can do is here. So suppose, so remember, so let's use the backcross. Okay, we use backcross for design for this study, and the total number of progeny produced from this backcross is n. We have this many progeny from this design backcross, and we all know how to calculate the R, right? So we have learned this. All right, and based on this R, for each pair, each gene pair, the 5 genes, for each gene pair, we can calculate the R, and we use the SAR value, the sum of the adjacent recombination coefficient, to help us to identify this order. So I hope I can put everything together in a whole picture, because this is what we learned today, right? Now, once we got this, we want to find the confidence whether these 2 genes are tightly linked or not. So what we can do is we can see we draw a large number of n. So remember, the total sample size is n, but we can do the sampling with replacement. We can draw a lot of like resample one, the first one, of sample size n. Suppose we have like this many progenies, like from this backcross, right? This is the n. Okay, now we can do the resampling. We can, the same n, but this is for the sampling 1. We can generate the same size n from this original. Any questions here? So this is the resampling, right? The bootstrap. All right, so what we can see is like, we got another resample, but this resample is very similar to the original sample, but they are not identical. Can you tell the difference? Because so the first resample of size n is from the original sample of size n. It's very similar. In terms of distribution, it should be very similar to the original sample, but they are not identical, right? All right. Now with the new resampled progeny, you can do the same thing. You can find that map. It could be like for the second for this resample, you find the same order for this 5 loci. Does that make sense? Or it could be slightly different because you see your resample, the first resample is not identical with the original sample. So it could be like maybe you got a different map like this. Could be, right? But it doesn't matter because this is a resample. Let's say this is the resample. Resample 1. Okay. Now, once you got this one, you just do the same thing. Got a resample 2. Resample 2. And this one can give you like maybe another order. Does that make sense? Yeah, I hope this makes sense to you.
Yeah, that makes sense.
Okay, and so on. So you can do, let's say 100 times, because it's easy right now. Like using the computer, so this is not a big deal. So you can easily like resample like 1,000 times. Okay, now let's see what happened here. So suppose you got like 100 times the new map, right? Because here you are only interested in the confidence between these two. So you want to see if these two genes are always placed together. So what you can do is like by looking at each of this resample, each of map from the resamples, you're gonna see out of this 100, how many times they're still together. Does that make sense? So suppose there's like maybe 97 times out of this 100, these two genes B and D are placed together. Then this will give you a high confidence, like your original map, which shows like B and D are together, is correct. Does that make sense?
Yeah, that makes sense.
Okay, very good. All right, I think, yeah, let's see, okay. I think I'm done with this chapter. So I try to like make up a little bit like what we left. But yeah, we're doing great. I mean, so I'm gonna stop here. And so any questions for today's lecture? Okay. I hope you enjoy it. The bootstrapping is, the resampling is a very, very useful strategy, because in most of the case, because right now like the economic like crisis, right? So it's very hard for us to get a good research grant to support. So even you get something, like they're always like cut. They only give you like 70% of what they promised in the beginning. So then you have to calculate your research budget very carefully. So sometimes you can only afford one single sample. Make sure you get a unbiased sample, the random sample from the population of interest. With your single sample, you can still do a lot of things, like because we have learned how we can do the resampling. And so with the single sample, you can easily calculate the statistic that you can use for the inference for your population, right? Make a general conclusion, but you still need to estimate the variance of your estimation. So the bootstrap and resampling the sampling with the replacement is the way that you can consider to estimate the accuracy of your estimation. Yeah. All right, I think the regular class time is up, so I'm going to use the next like maybe 10 to 15 minutes to help answer your question if you have any.
Yeah, I had one small question. I might have missed the small detail, but why do we go with the smallest SAR value to determine the order?
Okay, sure. Okay. So intuitively, let me show you why this is. Oops. Okay. Try to. So intuitively, I think this makes sense because, for example, let me use some numbers here. So suppose A and B is like R equals to this, and B and C is closer, so let's use this. Suppose this is the real situation, right? Okay, the RAB equals to this, and RBC equals to this. So based on the definition, so if this is the real situation, so the SAR ABC should be 0.24 plus 0.18, right? So which equals to 0.42, something like this. All right. However, if we want to calculate the SAR, let's say ACB. So by definition, this will be equal to the RAC plus RBC, right? RBC, we already knew this is the point. But how about RAC? So we don't know this, but definitely we know this value because A and C is far removed, right? So this value must be something, let's make it up. So it must be something like 0.3. So this is AC. All right, intuitively, so this will be greater than this. Does that make sense?
That makes sense.
Yeah, the wrong order will give you like a SAR value, which should be greater than the value of the right order. So yeah, intuitively like this, but we can use the definition to prove this is the case. Yeah.
All right, that makes a lot more sense. Thanks so much.
Oh, sure. Any other questions? Okay, very good. All right. So so last time I posted some like easy R code for generating the chi-square variable distribution. Yeah. When you have time, yeah, please practice. And so this Thursday we're going to continue our lecture, and also I will provide some like a practice in R, so it can help you to understand better our class material. All right. Thank you, everyone. All right. Yeah.
Thank you.
Thank you. Bye-bye.